All right, as we move along here, our next topic is frames of reference. Before we get into that, I just want to do a quick reminder of what we were talking about in the last video clip, which was space-time diagrams. So remember, the idea here is that we're just looking at motion along the x-axis, just in one dimension here, and we're recording certain events, perhaps flashes of light or just some moving object as it goes along. We're recording it at certain times, certain locations in the x direction, whether it's positive to the right, negative to the left. And then we have the idea of actually plotting this with time as a vertical axis. So again, if you think about horizontal slices here, the x-axis as drawn is what the x-axis looks like at t equals 0 seconds. And then we'd have another slice at t equal 1 second, t equal 2 seconds, 3 seconds, and 4 seconds, and so on and so forth with that. So if we were to imagine, let's imagine a situation where we have an object moving, and we're taking flash photographs of it and recording the position at given times, and we'll just pretend, say, at t equals 1 second, it was at position 1 along the x-axis, and so we put a dot there, a mark there. And maybe at 2 seconds, we saw that it is actually at position 2 along the x-axis. And at 3 seconds, it was position 3, and so on and so forth with that, if I can draw that more or less correctly there. And we also talked about the concept then of a velocity, that we can actually draw a line through these plotted points if we wanted to. And the velocity of an object when we do this plot is essentially distance traveled over elapsed time. So the distance traveled, sometimes we call this the run along the horizontal direction, the distance traveled divided by the elapsed time. So in this case, if I traveled 3 units, maybe 3 meters in 3 seconds, clearly the velocity would be 1 meter per second, 3 divided by 3. And so the slope of this line gives us an indication of the velocity. Now, technically, the slope is not exactly equal to the velocity, because let's look at another situation here. Let's say that in 1 second, it only went half a meter. And so in 1 second, it'd be right here. And then in 2 seconds, it was at 1 meter. And at 3 seconds, it was at 1.5 meters. So it's going at steady velocity there, a half meter per second. We can pretty much see that. Draw the line here. And that represents a different path for perhaps a different object or the same object second time around going at a different speed. And we see here that in the first case, it was going 1 meter per second. In the second case, it's going half a meter per second. So we can see that when the slope is higher, a higher slope, larger number for the slope, more vertical line, is slower velocity, a lower velocity. Versus if the slope of the line is lower, then we get a higher velocity. So when we do this type of plot, this type of space-time diagram with time being vertical, x being horizontal, the velocity, if we have a constant velocity object, we get a plot of it, and it's going to be a straight line. And the slope of that line is inversely related to the velocity. Okay? So large slope, which means it's more closer to the vertical, means a slower velocity. Smaller slope means it's closer to the horizontal, gives us a larger velocity. And intuitively, you can think about it just by thinking about what we're plotting here. Again, if in 1 second, so if I go up 1 second vertically, I move 5 meters, that would be a slope sort of like this, like that. And that's going to be a higher velocity. I've moved a larger distance in a given amount of time versus one of these other examples here. I've only moved 1 meter in 1 second or even half a meter in 1 second. Slope of those lines is more vertical and therefore a slower velocity. Just something to keep in mind, because when we do this later on and actually apply relativistic effects to these types of diagrams, it'll be important to remember that higher slopes, larger slopes, more vertical slopes mean slower velocity. And as you bend down this way, it represents a higher velocity object. Again, everything being constant velocity here. We're not going to deal with cases of acceleration. If you do acceleration, so the velocity is changing on an object, you get curved lines going in various directions, not straight lines like that. So just a reminder about Space-time diagrams, again, everything is in, the physical reality here is in the x direction, the horizontal direction. We're just plotting things along the x direction. The actual physical reality is not objects moving at some angle here, but just moving along the x direction. We're plotting their position in time, and therefore we get these straight lines representing different velocities as they travel along the x direction. Okay, so that's a little reminder about space-time diagrams. We're going to do some more of these in this video clip on frames of reference. But let's get to that. And I want to remind you, too, that I hope you did the little priming the brain exercise with the moving sidewalks and all that. We're actually going to really do that same sort of concept. Instead of moving sidewalks, we're going to use spaceships here. So let's imagine that we have the classic use of names here is Alice and Bob. They also use these things in cryptography. Alice and Bob sending messages back and forth to each other encrypted. Comes probably from A and B. Okay? So instead of just saying person A, person B, we give them names Alice and Bob. And if you don't like the names Alice and Bob, you can use your own names here if you want. So we've got Alice and Bob, and they're in spaceships. So each of them has their own spaceship. And let's consider Alice first. Okay? So I actually have Alice here and her spaceship. And what do these circles represent? Those circles are clocks. We talked about how to record events in space and time. We need essentially a measuring system and clocks at each of those points on our measuring system to measure time. Essentially, we have a lattice or a grid of clocks. So that's what this is supposed to represent here, this nice little stick with Alice's spaceship, A for Alice, of course, and the clocks along here. So as far as Alice is concerned, we'll just start off with her at rest. And she has all her clocks set up there. And so she can record any event that occurs along her horizontal axis here. So there's Alice. And now let's bring Bob into the picture. So Bob will have an orange spaceship here. And we can imagine that Bob is flying by Alice like that. She's just at rest. Bob flies by. And perhaps as he flies by each of her clocks, her stationary clocks, and remember, I should have mentioned, they're synchronized clocks. So all of Alice's clocks here record the same time. They're not out of whack or anything like that. As far as she's concerned, everything is good. So as Bob flies by, then we can see that perhaps as he triggers some sort of photograph for each clock, and so the record of his flyby past Alice here can be recorded on each of her clocks, and then she can go back later and say, okay, at t equals 3.2 seconds, he passed this clock right here, and then later on he was passing this clock here at t equals 8.9 seconds or something like that. And from that, she could figure out what his velocity is passing by her. So let's pause there for a second and actually do a space-time diagram of just Bob flying by Alice and her clocks here. So if we do that, we'll say, okay, so here's our space-time diagram. And by the way, we will nearly always assume, unless specified otherwise, that when they're together right here, that's t equals 0. Okay? So we can imagine he's coming in here, and they set their clocks. There's a clock on Alice's spaceship as well, not shown. So she has a clock at each point along her axis here. And so right here is t equals 0, and then as he goes along here, Alice's clocks measure his position at those times. So we'll always assume that when we're talking about Alice and Bob, their clocks are synchronized. Bob has a clock on his spaceship. She has a clock on her spaceship. They're all synchronized at t equals 0. So often we'll be starting at our point t equals 0 here. So this will be time for Alice and position for Alice as Bob flies along. And we want to plot Bob's path through Alice's space, as it were. So at t equals 0, they're right together. Again, right here, we'll start our clocks right here at t equals 0, and then as Bob goes on, the various clocks will record Bob's position. And remember, all these are synchronized, so maybe when right here he's at time t equals 1, so all Alice's clocks would read t equals 1 at that point, according to her. and then t equals 2, perhaps here, t equals 3, t equals 4, t equals 5. So what we get is, we'll use red a little bit here, so let's put some tick marks in, like that. So position 1, 2, 3, 4, 5, 6, and some times 1, 2, 3, 4, perhaps. So this is what Alice would record. Alice would record, again, we'll just say at time t equals 1, Bob was at position 1, clock number 1 there. So right here, I guess we'll put it in red. Been using red here. At t equals 2, he's in position 2. T equals 2, position 2. T equals 3, position 3, and so on and so forth. And again, assuming constant velocity, we'd get a line. If we did more recordings of all his positions, we get that line representing a certain velocity. In this case, 1 meter per second, perhaps, or something like that. Whatever our units happen to be. Maybe 1 mile an hour or 1 light year per hour per second, something like that. So there is his, by the way, we'll talk about light years a little later on in the course. You've probably heard that term. You may be a little fuzzy on exactly what it means, so don't worry about it for the moment. So just constant velocity for Bob here. And this is what Alice would observe. And just to sort of jump ahead in terms of what we're talking about here in terms of frames of reference, this is Alice's frame of reference. Alice's frame of reference is her sitting there with her clocks. As far as she's concerned, she's not moving. She can see all of her clocks in a line there. They have photo recording devices, so anytime something goes by and she needs to record an event at that location, she'll have a record of that at that clock. And she's watching Bob fly by here. So this is Alice's frame of reference, and Bob is traveling through Alice's frame of reference. And so Alice is plotting Bob's path through that. And so it's at 1 second he was at position 1, at 2 seconds he's at position 2, 3 seconds he's at position 3, and so on and so forth. And we indicate this is Alice's frame of reference, Alice's perspective, because we're saying here TA, T sub A, and X sub A. These are Alice's measurements of Bob's flight through her frame of reference. But we could also ask, well, what about Bob? What's he observing? If we're out there in space, there are no other reference points, we'll say, nearby. So as far as Bob is concerned, to Alice, Bob is flying by this way. To Bob, it's actually Alice who's moving that way. He sees her receding behind him. And so we could also ask, what would this be like in Bob's frame of reference? And in fact, just to make it a little clearer, Bob has his own lattice of clocks, which he can record anything in his frame of reference along the x direction, and each clock represents the time for him. All his clocks are synchronized. All Alice's clocks are synchronized. A little later on, next week, we'll see that that was one of Einstein's key insights, that Alice's synchronized clocks in this case, Bob has his synchronized clocks, but as far as Bob is concerned, Alice's are not synchronized, and also Bob's are not synchronized to Alice. But that's jumping ahead a little bit. We need to make sure we understand how these frames of reference work, because even though the idea is fairly simple, in my experience, I find it later on it can cause some confusion, like I've said before, if you don't get these foundational issues down solid. So, again, Alice sees Bob flying by. Bob, from his perspective, sees Alice receding, really flying by backwards, if you want to put it like that. And he can record Alice's path with all his clocks. And again, they're synchronized for him. Alice's clocks are synchronized for her. So if he did that, what type of diagram would he see here? Well, let's draw another one over here. And we'll label this T sub B, because this is Bob's perspective, Bob's frame of reference. And this is X sub B. And actually, in this case, we needed some negative values here, but we'll put these in. Right, 1, 2, 3, 4, -1, -2, and now we're running into Alice's plot there. And then the time again, 1, 2, 3, well, more or less. You see I've got different scales here, but we'll assume it's the same. Doesn't really matter for our point here, because plotting Bob, then he sees Alice, plotting Bob's perspective. Okay, remember, from Alice's perspective, at time t equals 1, he was at position 1. Time t equals 2, he was at position 2. For this simple example, we'll assume it works the same way for Bob. So he sees Alice at t equals 1. He sees Alice at his negative 1 position, and then negative 2 position, negative 3 position, and so on and so forth. And so we get something like this. At t equals 1, he sees Alice right there. And at t equals 2, he sees Alice here. And so, again, if we continued on, we get a line going like that. In other words, it's just pointing in different directions. It points to the left. This one points to the right because, as far as Alice is concerned, Bob is moving to the right. As far as Bob is concerned, Alice is moving to the left. And just to indicate this is Alice from Bob's perspective, from his frame of reference. And this is Bob from Alice's perspective. One moves to the left, one moves to the right. And the whole concept here of a frame of reference is that neither could tell which is really moving and which is stationary. Really the whole concept of the principle of relativity that we're working our way towards here, and we'll get to very soon, not quite in this video clip, but coming up in a couple video clips here, we'll talk more about that. But we can already see hints or indications of the principle of relativity here, that if you're out there in outer space, there and there are two spaceships, there are no other reference points around, one can't tell where the other is moving. And perhaps you've had that experience. You've ever, say, been on a train or even a car, perhaps, where there's another train or car next to you, and the road is very smooth, the tracks are very smooth, and so you see movement, and you're not sure, are you moving, or is the other train moving? And it can be disconcerting there for a minute. But that's really the key concept of the principle of relativity. Alice and Bob, Alice sees Bob moving, Bob sees Alice moving. As far as Bob is concerned, he's stationary. As far as Alice is concerned, she's stationary as well. So this is the frame of reference concept. The frame of reference is the perspective of a stationary observer like Alice or Bob with their frame of clocks. And so this is Alice's frame of reference. This is Bob's frame of reference with his lattice of clocks, synchronized clocks. And the whole idea here that we'll explore more as we go along in the course is some of the surprising results of the fact that even though it seems like if Bob's clocks are synchronized and Alice's clocks are synchronized, they should see things the same. In actual fact, they don't see things the same because of some surprising results due to the speed of light, as Einstein was really the first to understand that. Okay, so that's introduction to Alice and Bob and frames of reference. Let's do another few examples here, a few more examples to perhaps clarify things a little bit or just see if we understand them correctly. Okay, let's add another frame of reference here. We'll add Earth. So let's just say we've got okay, here's Earth, and we're going to imagine that Alice and Bob are back in their spaceships again, and they start off perhaps on a race or something, maybe not a race, but they're just flying around. And so here is Alice in her spaceship, and she's going with velocity v, and here's Bob in his spaceship, and we'll say he's going with velocity, if I can write it well here, 2v. Okay? Whatever the velocity is, Bob is going twice as fast as Alice. And so this is from now the perspective of Earth. Okay? Now let's pretend we're on Earth. We're the observer. We're watching Alice go by us at velocity v. Bob goes by us at velocity 2v. We also, on Earth, would have our lattice of clocks, again, an imaginary lattice or grid of clocks, but they would all be synchronized. So remember, that's what it means to observe something. If we say later on, where are Alice and Bob out here someplace, to figure that out from our perspective on Earth, from our frame of reference, it means our clocks out here take pictures at that point where Bob is or where Alice is, and so on and so forth. So we can pinpoint their location, and we can pinpoint their time, and that gives us a space-time event. Well, let's do a couple space-time diagrams here of what this, first of all, let's look at what this looks like from Earth's perspective. So we'll do that over here maybe. Okay, so we'll call this T sub E for the Earth frame of reference, and X sub E for the Earth frame of reference in terms of the position, so time and position with respect to Earth. And we don't need the tick marks here. We'll just do sort of a maybe not quite as precise here, but we'll get the essential details. So Alice is going along at velocity v, and as she goes along, each of the clocks here, Earth's clocks, take photos, the Earth frame of reference clocks, take photos. And so we'd see perhaps something like this, where we'll do red here for Alice going by. So we've got Alice perhaps going like this. And so that would represent her path along the x-axis in time. And then Bob, of course, is going faster. And so this is Alice. Bob is going faster than Alice, twice as fast actually. So his path, or his path would be along the x-axis here. But the representation of that in our space-time diagram, remember that lower slopes mean faster speed. He covers more ground in a given amount of time than Alice does. In fact, he covers twice as much. So at t equals 1 second right here, he's gone twice as far. So he's about right here, there, if that was 1 second. When Alice has gone this far, at this time, Bob has gone twice as far. So he's about right there. And at this time, when Alice has gone this far, again, he's gone twice as far. He's going twice the velocity, so it'd be maybe about right there, and so on and so forth. So this would represent Bob, his plot in the space-time diagram. And lower slope means faster velocity. So that'd be the Earth perspective. What would Alice see from her perspective? As far as she's concerned, she's sitting here. She may say, looks, as far as I'm concerned, we'll pretend she doesn't know if her engine is on or anything like that. She sees Earth going backwards, away from her, and she sees Bob going forwards, away from her to the right. So Earth is receding back to the left. Bob is going out to the right because, of course, Bob is going twice as fast as she is. So from the perspective of her cockpit, she sees Earth receding at velocity v. She sees Bob going away from her at velocity v as well, because the difference between their velocity, Alice and Bob's velocity, is just v. 2v minus v leaves us just v. So if Bob was going 20, we'll say 20 meters per second, then Alice is going 10 meters per second. That means Bob is going away from Alice at a net velocity of 10 meters per second. Or if Bob was going 30 meters per second, Alice would be going 15 meters per second. So the net velocity difference between them is 15 meters per second. So for Alice, let's do her plot here. So T sub A for Alice and X sub A for Alice's perspective. She sees Earth going backwards to the left in the negative direction at velocity v. And so that would look something like this. There's that line there. So that would be what Earth would look like from her perspective. And she sees Bob moving away from her at the same velocity but in the other direction. And so it looks something like this, roughly speaking. So there's Bob from Alice's perspective. Bob moving away at constant velocity, Earth moving the other direction behind her at constant velocity. What about Bob's perspective? Let's do one for Bob here. Let's try to make it straight, or straighter. Okay, so there's that. This is X Bob and T Bob. So this is from Bob's perspective, his frame of reference. So what does he see? Well, he's moving away from Earth at 2v, whatever v happens to be. So from his perspective, just sitting in his cockpit, he sees Earth going behind him, receding in the distance backwards at 2v. And what about Alice? Well, he sees her receding behind him. Remember, he's going faster than she is. So he sees her receding by him at a velocity v. So again, maybe if Earth is going, we'll use for our example here, very ridiculously small velocity, say 30 meters per second. So if Bob is going 30 meters per second, Alice is going 15 meters per second. So he'll see Earth going backwards at 30 meters per second and Alice going backwards at 15 meters per second, and you'll get something like this. So roughly like this. So this would be Earth from his perspective, receding backwards at 30 meters per second, or twice whatever the velocity is. And then Alice, if I can sort of get this in here like that. I'll just eyeball it there. Alice would be something like that from his frame of reference. So if you look at this, you say, oh, they're like mirror images of each other, Bob's perspective and Earth's perspective, which makes sense because Earth saw Alice moving away that way at v and Bob at 2v. If we flip the perspective to Bob, he sees Earth moving behind him at 2v, this one, and Alice moving behind him in the other direction at v. So it helps just to play around with these diagrams a little bit, make up little examples for yourself, see how these things work. I want to do one more thing to, actually we'll put one more thing on these diagrams and then we'll do one other example here to sort of have you think about things. But what if I were to plot, let's look at Alice's plot here. Where would Alice be on this plot? Okay, this is really her frame of reference. She's sitting in her cockpit. She sees Bob going away from her that direction. She sees Earth going the other direction. How would you plot her on here? Well, think about it. From her perspective, she's just sitting in her cockpit at position 0. So as time goes on, she's always at position 0 from her perspective. And so on a space-time diagram, the plot for whatever observer, really whatever frame of reference we're talking about, is just going to be at position x equals 0. And so at time t equals 1, whatever here, this is her position right here. And then the next time, here, and here, and here, and here. So in other words, that's her plot on her space-time diagram. She's sitting at position 0. Similarly, for Bob, same thing. He's sitting in his cockpit. I can't remember, did I lift up Alice before? Anyway, so here's Bob. He's sitting in his cockpit at position 0. So if he's recording his position, his little clock there too, that as time goes on, he just takes a photograph of himself, I guess, like in one of those arcade machines, and he says, okay, here I am. I'm at that position 0 the whole time. So that's his plot on there, on his diagram. And same thing on Earth. If we were the Earth observer and we had our lattice of clocks here, and we'd say, okay, let's record our position as time goes on. It's pretty trivial. We're always at position 0. And so our position here, or the Earth observer's position here, would be there as well. But note, of course, from another perspective, our position, from Bob's perspective, it's like that. From Alice's perspective, it's like that, and so on and so forth. Different frames of reference. So the physical events are exactly the same. We've got Earth, Alice moving away at v, Bob moving away at 2v, or from Alice's perspective, Earth moving backwards at v, and Bob moving forwards at v, or from Bob's perspective, Earth moving backwards at 2v, Alice moving backwards at velocity v. It's the same exact physical situation, but we have different perspectives, and so we end up with different space-time diagrams. We also have a fancy word, somewhat fancy word, for our plots here. These are called world lines. World lines. So it's, in this case, this is Alice's world line from the perspective of an observer on Earth, from the Earth frame of reference. This is Bob's world line. It's really tracking his position and time through the frame of reference of Earth, through Earth's space-time diagram. And the Earth observer is just, the world line for this Earth observer is just a vertical line here, never moves. Same thing for here, for Alice. We've got the world line of Bob from Alice's perspective. world line of Earth from Alice's perspective. And same way for Bob as well. We talk about world lines. So we talk about Bob's world line from Alice's perspective. We talk about Alice's world line from Bob's perspective, and so on and so forth. A couple other things just to know about world lines and space-time diagrams if you haven't figured it out yet. But anytime you have a vertical line, let's say I plotted something. Let's use this one down here, Bob's diagram here. So if Bob did a plot of some event and it looked like this, like that, that is the world line of an object in Bob's frame of reference that does not move. Because look at this. At every given time, it's at the same position. So a vertical line represents something that is not moving. So that might be maybe the tip of the front tip of Bob's spaceship. As far as Bob is concerned, he's in the cockpit. That's not moving from him. It's a fixed distance from him here. Maybe he's sitting in the cockpit right here, 1 meter ahead here, or a number of meters, not 1 meter, probably a little more than that. So 10 meters ahead of him is the tip of the front of his spaceship, and it's not going to be moving as far as he's concerned. It's always 10 meters ahead unless something terrible has happened to his spaceship. So vertical line represents something that just stays in the same place in that frame of reference. Just like Bob in the cockpit is staying in the same place at the 0 mark. Maybe this is the 10-meter mark they had there. Same thing for any of these other things. We could draw a vertical line, and that represents an object sitting at that location that is not moving in that frame of reference. But of course, in another frame of reference, it is going to be moving. The front of Bob's spaceship to Alice is going to be a line like that, in fact. And actually not quite exactly, because if you think about it, if this is 10 meters here, then from Alice's perspective, if this is Bob exactly in his cockpit, then the front of his ship is also going to be moving that, but just sort of 10 meters ahead of where Bob in his cockpit is. So that's a vertical line. What about a horizontal line? A horizontal line, as we've emphasized, represents everything that goes on in that frame of reference at that given time. So if I draw a horizontal line, we'll come over here to Earth's perspective here. If I draw this horizontal line right there, more or less, okay, that represents the time. We'll call that TE equals 3 seconds or 3 minutes or whatever it is. So this is the T equals 3 line. And if I look at everything along that line, that represents everything that happened from Earth's perspective at T equals 3 seconds. So Alice was at this position right here at T equals 3 seconds, whatever that mark is on the x-axis. Bob was at this position right here at T equals 3 seconds. Our clocks took a photograph at that point in time and noted their position. So a horizontal line represents everything that happens in that frame of reference at that particular instant in time. Vertical line represents something that is not moving in that frame of reference. It's staying in the same position. Diagonal lines represent things that are moving. If it's tilted to the right, it's moving off to the right. Tilt to the left, it's representing something moving backwards. If it tilts down more, it means it's moving faster. If it tilts up more, it means it's moving slower. Okay, so that's just application of what a frame of reference is, a definition of what a frame of reference is, and then looking at it from our space-time diagram perspective. All right, we've been talking about frames of reference and have a couple more things to do with them. First, I want to introduce the term inertial frames of reference. Where does that come from? You've probably heard the term inertia. It actually comes from the Latin word inerse, which can mean things like lazy. And how does that apply here? Well, it actually goes back to Isaac Newton's first law of motion, where essentially he stated that any object that is at rest or in motion, in constant velocity motion, its inertia is its resistance to its change of state. In other words, if it's at rest and you need to put it into motion, the more inertia it has, the harder it is to change it from rest to some velocity. Or if it's traveling with constant velocity, the difficulty you have in terms of actually changing it to a different velocity. So that's where the term inertia comes from, at least in physics terms. So we talk about an inertial frame of reference. For our purposes, what this will mean as we've been talking about Alice's frame of reference, Bob's frame of reference, an inertial frame of reference is a reference frame that's either at rest or in constant velocity motion, that there's no acceleration or anything else going on like that. And the special theory of relativity deals with inertial frames of reference. Later on, Einstein, about 10 years after the special theory of relativity, was able to put the final touches on his so-called general theory of relativity that dealt with non-inertial frames of reference. And that could be something where you're accelerating. But if you imagine, think about just being in a car, even as you go around a curve, you're sort of thrown to the outside. That's a non-inertial frame of reference. There's some acceleration involved in that circular motion or that turning. If you're going straight along in a car at constant velocity, you don't feel yourself pushed back in the seat or thrown to the side. So that's one piece of evidence that you're in a non-inertial frame of reference if you feel that acceleration, if you feel yourself being pushed back in the seat, or if you feel yourself going around a curve, thrown to the side, and so on. So, or actually, a gravitational field is a non-inertial frame of reference. But that's beyond our course. That's the general theory of relativity, as I mentioned. So in this course, anytime we talk about a frame of reference, we will assume it is an inertial frame of reference unless otherwise specified. So again, inertial frame of reference just means it's either at rest or in constant velocity motion. So we can talk about one frame of reference, maybe Alice's versus Bob's frame of reference, and we know they're inertial if the motion between them is just constant velocity. There's no acceleration going on. So inertial frames of reference. Other thing we want to mention here is combining velocities. Now, everything we're doing here is actually before pre-Einstein, so we haven't got into that yet. So this is combining velocities in what we would say at the low velocity limit. When velocities are low enough, not near the speed of light, then everything we've said so far applies. Again, we'll see how it changes when we get to Einstein's principles and his two key principles we'll be getting to, and then the implications of those as he worked them out. But so combining velocities, let's just do a little example here. Let's say we've been talking about Bob and Alice. So let's go back to Bob's spaceship here. So here's his spaceship with his cockpit. And he's going, Alice is observing him, so maybe he's going by with some velocity v. Now remember, for Bob, as far as he's concerned, he's not moving. He has his whole grid or lattice of clocks all synchronized with each other, and so he can measure events in his frame of reference. He's an inertial frame of reference because, as far as he's concerned, he is at rest there, and he can tell that because he doesn't feel any acceleration going on. So he has his lattice of clocks there, and we're going to imagine here that he has a spaceship such that if something goes wrong, he has an escape pod. And so, we'll just put not a very fancy spaceship here, but we'll assume the escape pod is just that spherical object there. And so if necessary, he can get in that escape pod or put something else in that escape pod and have it shoot off from his spaceship. And so we're going to assume that if he does that, it will shoot off from his spaceship at a velocity v. So know what's going on here. From Alice's perspective, from her frame of reference, Bob is traveling by at velocity v, but he's also shooting off his escape pod at velocity v. So let's back up to Bob's perspective. From Bob's perspective, he's just sitting there in his cockpit. He actually maybe sees Alice going, receding in the background from him, but he assumes that she is in motion, not himself. He assumes he's at rest. You can see all his lattice of imaginary clocks, as it were. And so he shoots off his escape pod at velocity v. So he sees that escape pod going away from him at velocity v, and he can measure that on his clocks and his measuring apparatus there. So what does Alice see? So here's Alice here. So there's Alice. She's observing Bob go by. The question is, what velocity does she see the escape pod going at? Well, very simply, we just add the velocities. And so if the escape pod is receding from Bob's ship at velocity v, going away at velocity v, and then from Alice's perspective, Bob's ship is actually going at velocity v, then the velocity of the escape pod to Alice, equals v plus v, which of course is 2v. And we've chosen the same velocities in this case, but it works for any velocities. We could say, maybe the escape pod is shooting off at 3v, and Alice sees Bob going by at velocity v, then it's v plus 3v, and you get 4v. So that's the velocity of the escape pod as Alice sees it going along there. If you want maybe a more prosaic example, think about it if you're throwing a ball, throwing a baseball or something like that, and maybe you can throw it at 50 miles an hour if you want 50 kilometers per hour. Obviously, they're different, but just pick whichever set of units, system of units you want there. So you can throw it at some velocity to your friend over there who's catching it. And then you get on a truck or something like that, or even a bicycle, or just even running toward them. And then you throw it at the same velocity. So the velocity then of the ball coming toward your friend is going to be the velocity of the throw itself, assuming 50, plus whatever velocity you're either running, riding on a bike, on a pickup truck or something. Obviously, don't try this at home perhaps, or be very careful if you do things like this with moving vehicles. But the person who's catching the ball is going to see that added velocity. It's going to be the velocity of the moving vehicle, whether you're just running or whether it's a bicycle you're on or some sort of car or truck. And as you throw it to them, you throw it with the same velocity. In other words, it's leaving your hand with the same velocity, say 50 kilometers per hour. But then the velocity of your movement as well adds to that, and so your friend has to catch it at a higher velocity there. Or if you go the other direction as well, if you're going away from your friend at, say, 50 kilometers per hour, and you're throwing it toward him or her at 50 kilometers per hour, it cancels out. So we've got 50 going that way, you're throwing 50 that way, and the ball, in principle, just drops straight down. In fact, if you ever watched the show Mythbusters, they tested that one time, and it took some doing to get everything set up right, but they were able to get at least one case where they had perfect velocity of the truck going by this way. They had a little apparatus that shot out a basketball or something like that. And so when they were able to shoot it with this velocity and cancel it out with the velocity of the truck going the other way, and using the high-speed camera, they saw the basketball just drop straight down. So that's the idea here, that when you're combining velocities in frames of reference, the velocities just add. So again, in Bob's frame of reference, he shoots out his escape pod with some velocity. In Alice's frame of reference, she's at velocity v. In this case, the escape pod is moving away from Bob at velocity v, and so to Alice, the escape pod is moving at velocity 2v. Or again, if it's going in the other direction, it would cancel out. So if Bob was moving with v this way and he shot the escape pod the other way at velocity v, the escape pod to Alice would just sit there. Again, to Bob, it'd still be going away from him, but to Alice, the movement of the spaceship that way plus the escape pod that way would mean the escape pod would just sit here in her frame of reference. So that's how we add velocities before Einstein came along. And as we will see with his two key postulates or principles of his special theory of relativity, which will be coming up here in a video clip or two, I think 2 video clips away now. We'll talk about those in more detail. Some of the implications of that are this doesn't work. It works for low velocities that we encounter in, for the most part, everyday life. But once you get up to velocities near the speed of light, you can't just add things like this. So if Bob's velocity here is near the speed of light, his spaceship is near the speed of light, and he shoots off his escape pod at some velocity v, it's not just as easy as this. It's not a simple combination, a simple addition of velocities. So that's one of the things we are heading towards. In the next video clip, we'll want to say a few more words about things with frames of reference and space-time diagrams, and then we'll get on to Einstein and his two principles on which he based his special theory of relativity.